needs or the activities of a particular set of users or applications. The nice thing about the DBMS approach or the database approach is that those views can be defined, stored in the catalog, and then subsequently used. We don't have that in the file-based approach. In the file-based approach, if you would like to define views, it would require copying files, it would require copying parts of files, and any changes made to those duplicates should be carefully merged in all the other duplicates. Databases are also more and more used in a distributed environment. Databases will typically become more and more accessible in a World Wide Web environment on the internet. That means that we should have facilities for concurrent access. Right? Multiple users should be capable of simultaneously accessing the data in the database. Well, for this, DBMSs will include facilities for concurrency control to ensure that no conflicting operations are executed. Imagine that you have a database application in which you have a bottle of wine. You only have one particular bottle of wine. You put it on eBay, so multiple users can actually simultaneously access the bottle of wine. But as soon as one user makes the purchase, the bottle of wine is no longer available to the other user. So you have to make sure that only one user can make the purchase and not two people purchase that one bottle of wine, because that's simply not possible. So in order to achieve that successfully, the DBMS needs to have facilities for concurrency control. In a file-based approach, this becomes a lot more complicated. In the file-based approach, it is nearly impossible to have people or applications working on the same file. Those facilities for concurrency control are not available. So, in a nutshell, DBMSs have catalogs. This is not available in a file-based approach. DBMSs or databases have program data independence. In a file-based approach, you have program data dependence. In a database approach, you can have the idea of views, which you do not have in the file-based approach. In the database approach, you have facilities for concurrency control, which you do not have in the file-based approach. Here you can see the DBMS or the database approach to data management again visualized with our previous example. So we have an invoicing application, we have a CRM application, customer relationship management application, we have a GIS application. All of them are going to work by means of the DBMS software. DBMS software, which is going to include both raw data and a catalog. Remember, the catalog contains all the metadata. So it contains all the data about the data descriptions, the constraints, and so on. And the catalog is one of the key differences between a database approach to data management and a file-based approach to data management. In what follows, we're going to zoom into some of the elements of a database system. First, we're going to talk about data models. Then we're going to talk about schemes and instances. We're going to extensively outline the tree scheme architecture. We're going to talk about data dictionaries. A data dictionary, also referred to as a catalog. So data dictionary and catalog are synonyms. And then we're going to discuss about DBMS languages. Data models are very important in this course. Basically, in subsequent chapters, we're going to discuss different types of data models. And what's a data model? A data model is a collection of concepts that can be used to describe the structure of a database, the data types, relationships, and constraints. Let's illustrate this with an example, again with the university application. So there we have the different types of concepts. So we have a student concept, we have a professor concept, we have a course concept, we have a building concept. And we're going to discuss those concepts and model what kind of information we want to gather about each of those concepts. So for a student, we want to gather student number, we want to gather student name, student address, student gender, etc. For course, we want to gather course number, course name, study points, etc. We're also going to discuss the data types. The data types are how the information should be represented. Student number is an integer. Student name is a string. Student email address also has a particular data type. So it's just like a set of characters followed by an @ sign, followed by a set of characters, followed by a dot, and then ending in com.com.be, whatever. You also have relationships which you're going to capture in your data model. So Students can take courses. Courses can be followed by students. Professors can teach courses. Courses can be taught by professors. And you also have constraints. A professor should teach at least one course. It's a constraint. A course should be taught by at least one professor. That's a constraint. A student should take at least 60 study points or courses during an academic year. That's a constraint. So all those information elements, together with the data types, the relationships, and the constraints, should be appropriately captured in the data model. Data modeling will be a key activity in this course. And a data model is typically something which is being made between a business analyst or a business user, I would say, let's call it a business user, and a data modeler. The business user is the person that is going to use the database application and that understands the business problem. The data modeler is the person which is going to make the data model and that wants, and he or she wants to understand the business problem to make sure that the data model is as accurately as possible a reflection of the underlying business problem. You want to capture the information needs as accurately as possible. And there exist different types of data models. The first type of data model is a conceptual data model. Conceptual data model is a high-level model. High level, that means it's very user-friendly. It is not very specifically oriented towards implementation. So it contains high-level concepts. It has a representation of part of the reality, and it's close to how the user perceives the data. Types of data models, well, we have the EER model. That stands for Enhanced Entity Relationship Model. We're going to extensively comment on that in due course. And object-oriented models. These are two examples of conceptual data models that we're going to come back to. Next to that, you also have data models which are going to be more implementation focused. Here we're going to discuss concepts that may be understood by end users but are not too far removed from the physical data organization. So we're getting closer and closer to the implementation here. They're going to hide some details of data storage but can be implemented on a computer system in a direct way. So those models are technically a little bit more detailed than the conceptual data models, which are more high level. Examples of implementation data models are the hierarchical model, the network model, the relational model, and the ODMG model, which we're again going to come back to later on. The physical data model is then really the lowest you can go in terms of implementation, because here we're going to have a low-level model that is going to describe the concepts and the data's physical storage details. Here we're really going to describe how the data should be physically organized. And the way you're going to do data modeling typically is that you're going to start from a conceptual data model, very high level, and you're going to make it more and more implementation specific. You're going to make it more and more specific to the physical environment until you end up with a physical data model. Also very important is the concept of schemes, instances, and a database state. In every database application, it is very important to distinguish between the description of the data, the metadata, the data definitions, the data structures, constraints, etc., and the data itself. A database scheme is a description of the database. So it's basically the metadata. It describes the data structures, the connections between them, and so on. And typically, this is specified during database design and is not expected to change too frequently. So here, we're again talking about those data definitions like professor, students, course, building, the relationships between them, and all the data items that we want to capture about them, student number, name, etc. All of that needs to be specified during database design, typically in collaboration between the business user and the data modeler. And once both of them have agreed upon those definitions, we will store them in the catalog. Remember, the catalog is a very essential part of the database approach towards data management. So this is the database scheme. The database state is then the data in the database at a particular moment, which is also called the current set of instances, the current set of observations. It's the data currently in the database. So let's just illustrate that. Here you can see a database scheme. You can see some data definitions. So we have a student information concept, which has number, name, address, email, course, number, name, and building number and address. Now, this is something which is going to be static. That means that it's not going to change too frequently. It may change. For example, at some point, you also want to include the student's Facebook account or student's Twitter account or LinkedIn account in the database, but those changes will not occur quite often, every now and then. Here you can see the database state. The database state means the status of the database at a particular moment in time. So you can see a student table with particular students in there. You can see a course table with particular courses in there. You can see a building table with all the buildings in there. This is going to be a lot more volatile in terms of content. So when a new student gets registered, you need to add them to the student table. When a student's going to change address, you need to change it in the student table. When a course gets removed, since it's no longer offered, you need to remove it from the course table. So you see, this is going to contain information that is a lot more volatile. A lot more volatile when compared to the database scheme. The database scheme, data definitions, are typically considered to be very static, whereas a database state, is going to be very volatile. A very important architecture underlying any database application is the tree scheme architecture. Here you can see the tree scheme architecture visualized. We're going to start at the middle. The middle is the conceptual scheme. This is going to involve all the concepts about which we want to gather information. So here you have those concepts like student, you have the concepts like professor, building, and course. And there you're going to model all these concepts. You're going to say what information we want to gather about students, what information we want to gather about courses, what information we want to gather about buildings, and what are the relationships between them. Okay? That's a conceptual model. Now that model needs to be physically implemented at some point. At some point you want to have an internal scheme. Internal means a physical scheme which is going to discuss the physical implementation of that model. So some information may be stored in files, some information may be stored on disk or in the cloud. So you have different ways of physically storing the information. And basically what you want is you want to have physical data independence here. That means both layers, the conceptual layer and the physical layer, should be as independent as possible, such that if you make a change to the physical layer, it should have no impact on the conceptual layer. The external layer gives us the views. Now, what is a view again? Well, a view is a subset of the information in the conceptual level, tailored towards the needs of a particular set of users and or applications. You can have one view which offers you information tailored towards the needs of professors. Another view which is going to offer you information tailored towards the needs of students, and another view which is going to offer information tailored towards the needs of educational program assistants, for example. Now again, you want independence between the external layer and the conceptual layer. So three-level architecture should be built in such a way that you have as much as possible independence between the layers. Imagine that you would do a change at the physical layer here. That means you would physically reorganize your data. Then the above layers should not be affected. If you change here at the conceptual layer, if you add another type of concept about which you want to store information, then your applications, which are going to make use of the views to access the data, should remain unaffected. So this is a very flexible architecture which is going to give us very performing applications. Let's have a closer look here. The external view, or the user views, are situated, of course, at the external layer, and an external view or scheme is going to describe the part of the database that a particular user group is interested in. Particular user group, professors, students, educational program assistants. And it's going to hide the rest of the database from that user group. So by means of a view, you can kind of shield information from particular user groups. Students should not have access to professor information. They should not have access to a professor's salary, for example. So you want to make sure that that information is shielded from students. Professors should maybe not have access to certain type of personal information about students, like medical information that might be stored. Okay? So that can be nicely implemented by means of the views. Views will allow you to actually offer information to specific groups of users and hide from that particular group of users information that is of no relevance to them. So those views can be typically described using a high-level data model or an implementation data model. And we're going to give some examples of how you can create views in what follows. Conceptual scheme is going to specify objects, students, professors, courses, buildings, characteristics of objects, student number, student name, relationships between objects. A student can take courses, a course can be followed by students. Integrity rules, like a professor means it's a physical organization, so it's going to specify how the data are physically stored, how we can optimally access them using indexes, access paths, etc. A key advantage of using that three-level architecture is independence. So we want to make sure that changes in one layer should only have minimal impact on all the other layers. So if we make changes in the physical layer, we want to make sure it has almost no impact on the conceptual or external layer. If we make changes at the conceptual layer, it should have no impact on the external or view layer. So that's what you want to actually aim for. Here you can see that again visualized in a particular company setting. So imagine that you have some departments that need certain types of information. They need product information, customer information, invoice information, delivery information. And imagine that for products that we're going to store name, description, and cost. For customers, we're going to store name, phone, and address. We store certain types of information for invoices and delivery. So what information that we're going to store for each of those items is specified at the conceptual level, together with the relationships between all those concepts. How it is physically stored will be specified in the internal or physical scheme. So here you can see that certain information is stored in London, in Washington, and Moscow to make sure that from an international perspective, a worldwide perspective, we can have fast access to the data. Here at the external view level, you're going to see the information as it is being offered to some of the departments and tailored towards the needs of some of the departments. So we're going to have some information that is tailored towards the needs of the finance department. That particularly relates to invoicing information where we need product, amount, price, and date. We're also going to have some information that is tailored towards the need of the customer service department. Customer service department wants information on customers like address, phone number, ordered product, delivery address, and so on. And then we have the logistics department, which will need information particularly pertaining to delivery, date, address, product, and amount. So you can see this is nicely implemented by means of the views. The views are actually, as I said before a couple of times already, the views are actually going to tailor the information towards the needs of the particular department, towards the needs of the particular set of business users. The data dictionary or catalog, those are two synonyms of one another, is the heart of the database system. The heart of the database system, since it contains all the metadata. It's going to contain all the data definitions, the data types, the data structures, the constraints, and so on. So it's going to contain actually the definitions of that three-layer architecture. It's going to contain the definitions of the conceptual scheme, which was the scheme in the middle. Remember, the external view or user views, which was the scheme above, and it's also going to contain the definitions of the physical scheme. In order to appropriately implement this, we will need DBMS languages. Languages that will allow us to define all these concepts, that will allow us to define all these constraints, and that will, of course, also allow us to define those three levels. And DBMS languages can be categorized into two types. First of all, we have a data definition language, or DDL. This is the language used by a database administrator, or DBA. The DBA is the guy which is going to actually work with the database, which is going to set up the database, monitor, and maintain the database. So by using DDL, the DBA can define the database conceptual, internal, and external schemes. So it's a set of language instructions that will allow us to do that and store the results of these instructions in the catalog. DBMS languages also involve data manipulation languages because obviously we do not only want to define the data structures, but we also want to manipulate them. So here we have the language used to retrieve, query, insert, delete, and modify the data. And those DBML statements can be entered either interactively from a terminal, from a computer. You just enter your DML statements interactively, like you do in Microsoft Access, where you can formulate SQL queries, for those of you who are familiar with that. or in a general purpose programming language. In a general purpose programming language like Java, you can directly embed DML statements in the language. DML statements which are then going to set up a connection to a database, which are going to query information in the database, update, delete, or insert information in the database. The most popular example of a DBMS language is SQL. SQL stands for Structured Query Language, and it has both DDL and DML instructions. You can use it both interactively, interactive SQL, or embedded in a program environment, embedded SQL. In one of the later chapters of this class, we're going to extensively comment on SQL, and we're going to go through the whole SQL syntax. We're going to discuss how you can define data elements, how you can define queries, how you can work with queries, etc. So these are languages which will be used a lot by database designers, definitely also by database administrators, also by programmers that want to work with databases, but also by end users. End users are people that actually are going to use the database application, and it's very important that they know SQL because that will allow them to formulate queries which are tailored towards their needs. So if an end user wants a particular piece of information, you can formulate it as an SQL query and ask that information then from the database. Okay, so now we have discussed the elements of a database system. Now we're going to look into some of the advantages of using database design. You can see the advantages listed here. First of all, there's data and functional independence, which is a very important advantage when working in a database environment. Then we have database modeling, managing data redundancy, specifying integrity rules, facilities for data security, backup and recovery facilities, and performance utilities. First of all, data independence. This is really a very important advantage of working with a database approach to data management. Basically what it says is that software applications should not be changed when changes occur to data definitions. And when I say changes occur to data definitions, those changes can occur at two different levels. They can occur at the physical level. Imagine that at the level of the physical database model that you're making some changes there. You're changing the physical organization of your data. You're actually storing information instead of in Brussels. You decide to store information in Brussels and New York because that may speed up your applications. That's a physical data change, but it could also involve the definition of a new access path, way of accessing the data. It could also involve the definition of a new index. An index is like a fast way to find information. It could also involve different kinds of storage media. Maybe at some point you decide to store information in the cloud, for example. Well, actually, physical data independence means that if you make those changes at the physical level, your applications will remain unaffected. They will keep on running. And if you're lucky, they will run faster. So by adopting physical changes, you can have physical data independence. Your applications will keep on running, and they might even run faster. And in order to achieve that, the DBMS is going to provide interfaces between the conceptual and the physical model. Logical data independence is another type of data independence, which means that software applications must not be changed when changes occur in the conceptual scheme. So when we make changes to the conceptual scheme, the concepts, those changes can be made and the software applications will keep on running. Imagine that at some point you want to gather more information about your students. You want to add one piece of information to the student concept, like social media account, Facebook page, Twitter account, or LinkedIn account. Well, you can add that change to the conceptual model, and your software applications, which are going to make use of student information, they will keep on running. So they will not be affected. That's the idea of logical data independence. So whether you add new objects or whether you add new characteristics to objects, Facebook or social media account to students, for example, if you do that in a conceptual scheme, it will have no impact on the software applications because basically the conceptual scheme is hidden from those software applications by means of the views. So the views are going to offer the information tailored towards the application such that changes in the conceptual scheme will not affect any of the applications. To that end, the DBMS will provide interfaces between the conceptual scheme and those external views. Another very nice property is functional independence. And nowadays, if you look at many database applications, databases are going to store more and more small pieces of functionality, small procedures. This is especially the case in object relational databases and object-oriented databases, which will also be discussed in this class. Now, what is a function? A function basically has two parts. It has an interface or signature, which is the name of the function together with its input parameters, its input arguments that are needed to perform or calculate the function. A function also has an implementation or method, and the method is basically going to specify how the function should be executed. Let's give an example of a function. Here you can see a function calculates